Hello everyone, this is another video of circuit synthesis problem. In this video, I will explain how to construct a LC circuit using a given net impedance function. For, for this one, I use first Foster form and second Foster form. In Foster form, we are using partial fraction expansion. For the first Foster form, we are using partial fraction expansion of a impedance function. And for the second Foster form, we are using partial fraction expansion for the admittance function. The function is impedance, then we have to convert it to the admittance value. Before going to construct the circuit, we have to check this function is realizable or not. For that one, we have to check some properties of passive RLC functions. These are some properties. First one is must be a rational function in S with real coefficient. You can see in this function there are terms and all are real coefficient. Then first condition is satisfied. And second one is may not have poles or zeros in the right half S plane. For that one we have to find poles and zeros. The poles, we can obtain poles from the denominator. We can rewrite this function again, s squared plus 1 s squared plus 3 over s times s squared plus 2. From the denominator, we can obtain 3 poles, s equals 0 and s is equal plus or minus root 2j. These are the poles, and we can obtain zeros from the numerator. S is equal plus or minus j and s equal plus or minus root 3j. These are the zeros. When I plot the poles and zeros in complex plane, this is real axis, this one is imaginary axis, poles at origin and at root 2 plus root 2 and minus root 2. These are poles and zeros at plus 1 and minus 1. Another two poles at root 3 and minus root 3. This is a 0. Then this is the right half plane. You can see there are no any poles or zeros in right half S plane. Then second one is satisfied. Third one is may not have multiple poles or zeros in j omega axis. You can see there are no any multiple poles or zeros. And fourth one is may not have degree of the numerator and denominator differing by more than 1. In this function, degree of the numerator is maximum 1 is 4 and the denominator maximum 1 is 3. The difference is 1. It is not more than 1. And next one is must have a non-negative real part for s equal j omega. For that one, we have to assign s equal j omega to the function. Say del c j omega is equal to j omega to the power 4 plus 4 into j omega squared plus 3 over j omega cubed plus 2j omega. Then omega 4 minus 4 omega squared plus 3 over j into omega 3 minus omega 3 plus 2 omega. You can see this denominator is a imaginary one, then real part of the Z del C j omega function is equal to 0. Then this one also satisfied. It is non-negative. And last one is must have a positive and real residues for poles. For this one, these are the poles, s equal 0 and s equal plus or minus root 2j. For that one, we have to do the partial fraction expansion. In first of all, also we have to do the partial fraction expansion. Now I will do the partial fraction expansion. Set LC s equal to x to the power 4 plus 4s squared plus 3 over s times s squared plus 2. In here, degree of the numerator is greater than the degree of the denominator. Then we can write the partial fraction expansion as plus b over s plus cs plus d over s square plus 1. Sorry, 2. Then we have to find value of a, b, c and d. S to the power 4 plus 4 s squared plus 3 is equal to s times s cube plus 2s plus b into s squared plus 2 plus s into cs plus d. Then I can find these values. If we consider s to the power 4, from the left hand side, value is 1. From the right hand side, value is a. For the s to the power 2, from the left hand side, 4 is equal to 2a plus b plus c. Value of a is equal to 1, then 2 is equal to b plus c. Then s to the power 0, 3 is equal to 2b. Value of b is equal to 3 over 2. From this one, c is equal to 2 minus 3 over 2. It is equal to 1 over 2. And when I consider the s terms, 0 is equal to d. Then these are the values of a, b, c and d. This is value of a, value of b, value of c and value of d. In last property, it says must have positive and real residues for poles. In here, real residues are b, c and d. You can see value of b, c and d are positive and real. Then last condition also satisfied. Then we can apply the first form to this function. And also there are some additional properties for LC driving point function. The first one is function must be a ratio of odd even or even odd polynomials. In the here you can see in the numerator these are the even values. This is s to the power 0 and denominator is s to the power 3 and s to the power 1. It is a ratio between even and odd. Then first one is satisfied and second one is poles and zeros lie on the imaginary axis and are simple. You can see all the poles and zeros are lie on imaginary axis and They are simple. And third one is highest power of the numerator and denominator should differ by unity. Highest numerator value is 4 and the denominator value is 3. Difference is 1 and the lowest power also, lowest numerator value is 0 and the denominator value is 1. The difference is 1. Then it is also satisfied. And the fourth one is must be a pole law 0 at the origin and infinity. In here you can see a pole at origin. Then this one also okay. The last one is the poles and zeros alternate. In here you can see pole 0, pole 0. So from this side, minus side, pole 0, pole 0. They are alternate. Then we can apply the first form and second first form. In first form, we are applying the partial fraction expansion for impedance function. Then we did the partial fraction expansion. Then I can write value of A is 1. S plus 3 over 2 S plus half S over S squared plus 2. This is the partial fraction expansion of the given impedance function. These values are in small impedance values, Z1, Z2, and Z3. Now we have to check what are the elements for each and every impedance part. If we consider a inductor, value of L, impedance of an inductor is Ls, and admittance of an inductor is 1 over Ls. If we consider a capacitor, impedance of a capacitor is 1 over Cs and the admittance of a capacitor is Cs. We can use these terms to obtain the final circuit. If we consider Z1, it is equal to S. That means it is a inductor. L1 value is 1. Z2, it is similar to capacitor. I can rewrite this 1 over 2 over 3 S. Then it is a capacitor. C1 value is 2 over 3 farad. And Z3 1 over S over S square plus 2S square plus 4. For this one, I consider admittance value Y3, then 2S plus 4 over S. For this one, this is admittance value. When I consider the admittance value of a capacitor, it is like to this term. Then it is C2, value is 2 farad. And when I consider this one, I can rearrange it as 1 over 4 S. It is more like to a inductor. L2 value is 1 over 4 Henry. This is a combination of two admittance. Then these two elements are connected in parallel. C2 and L2. Then here these are connected in series. Then final circuit we can draw. First element is inductor, L1 is 1 Henry. Second element is a capacitor, C1 is 203 Farad. And the third one is parallel connected capacitor and inductor. C2 is 2 Farad. L2 is 1 over 4 Henry. We can obtain the total impedance from these 2 points. And final circuit will be like this. It has 2 inductors and 2 capacitors. Then we have to do the second Foster form. For this one, we have to consider the admittance value. When I consider admittance value, the function like this, s to the power 3 plus 2s over s to the power 4 plus 4s squared plus 3. If we consider the general properties of RLC function for this admittance function, you can check these all conditions. In here, poles and zeros are interchanged. Now we can do the partial fraction expansion. This is second Foster form. Y LCS is equal to the power s to the power 3 plus 2s over s to the power 4 plus 4s squared plus 3. We can write for this term, there are two roots, s squared plus 1 and s squared plus 3. Then we can write as plus b over s squared plus 1 plus cs plus d over s squared plus 3. Then s cube plus 2s is equal to as plus b times s squared plus 3 plus cs plus d times s squared plus 1. From this one, I can consider s to the power 3 terms. From the left hand side, value is 1. From the right hand side, value is a. From this one and from this one, plus c. Then I consider s to the power 2. From the left hand side, value is 0. Right hand side, b plus d. Then s to the power 1. From the left hand side, 2 is equal to, from the right hand side, 3a plus c. And s to the power 0, from the left hand side, value is 0. From the right hand side, 3b plus d. From these two, value of c is equal to 1 minus a. Then 2 is equal to 3a plus 1 minus a. 1 is equal to 2a. Then value of a is equal to half. And also c is equal to, from this one, c is equal to half. Then from these two, we can obtain value of b is equal to 0 and d is equal to 0. Then we can write the final partial fraction expansion. Half s squared plus 1 plus half s square plus 3. This is the partial fraction expansion of this admittance function. These are small admittance value y1 and y2. First, I consider the y1 is s over 2s square plus 2. I consider the impedance value. It is equal to 2s plus 2 over s. This is more like 2. Inductor, one value of 2 Henry. For this one, I can rewrite 1 over 102 S. It is a capacitor, value of 2, half. Then I consider the y2. It is s over 2s squared plus 6. Same as previous one, I consider the reciprocal of this admittance value. I said 2 is equal to 2s plus 6 over s. Same as previous one. This one is equal to inductor L2, 2 Henry. This is equal to a capacitor. C2 value is 1 over 6 farad. So this one we can rearrange 1 over 6 times S. Oh, when we consider these two elements, these are impedance value, then these two elements are connected in series, C2 and L2. Same as this one, they are connected in series, L1 and C1. The total one is admittance value, then they are connected in parallel. Then final circuit will be inductor, capacitor are series connected. C1, L1 is 2 Henry, C1 is half farad, and L2 and C2 are again connected in series. L2 also 2 Henry, C2 is 1 over 6 farad. This is the final circuit. We can obtain the final admittance value from these 2 points. YLC, yes. This is the way we are using second first of all to construct the given LC, construct a circuit from a given admittance function. I hope you all are clear about this example, how to use first form and second first form. Thank you.